This is Unit 10, Haloalkanes and haloarenes for NCERT, Class 12 Chemistry. This is Part 2. In previous class, we studied a little bit about haloalkanes and their nature, like what are haloalkanes and haloarenes, how they are classified, and we will study a little bit about allylic halides, benzylic halides, vinylic halides, and aryl halides. When a halogen connected to sp3 carbon or sp2 carbon. And today we're gonna start with the nomenclature. For halogenated compound, the common names of alkyl halides are derived by naming the alkyl groups followed by the name of the halides. In the IUPAC system, we are the nomenclature. When we say a nomenclature, it's always about IUPAC in organic chemistry. So the common names of alkyl halides are derived by naming the alkyl groups followed by the name of the halides. For example, let's see a compound with the 3 carbons, CH3, CH2, CH2, Br. So as I said, the common names of alkyl halides are derived by naming the alkyl group followed by the name of the halide. Okay. So if you number this 1, 2, 3, it's a 3 carbon. We are numbering the carbon on the right side as 1 because that's where you have the substitution bromine. Okay. So the name of this compound will be 1-bromo. It's a 3 carbon, right? 1, 2, 3. 3 carbon means it's a propyl, right? It's a propyl and it's a N-propyl because it's a single chain. It's not a it's connected at carbon 1. So how do we name when it's an IUPAC name? Okay, the common names are derived by naming alkyl group followed by name of the halide. So common name is the alkyl group comes first, alkyl, which is N-propyl, and halogen is bromide, right? So this is common name. Now for IUPAC, it's a bromo. For IUPAC, the alkyl halides are named as a halo-substituted hydrocarbons. So it's known as bromopropane, and the bromine is at first carbon, so it's going to be 1-bromopropane. Okay. So following the same rules, let's look into another example. CH3, CH3, and bromine at this carbon now. Now let's number 1, 2, 3. Now what would be your IUPAC? Let's look into the IUPAC names. Okay. So the alkyl halides naming will be haloalkanes. So this is something you guys need to remember. They are going to be haloalkanes. Okay. So what is your halogen here? It's a bromine, and it's at a 2, carbon 2. So it's a 2-bromo. And what is your alkyl chain? Alkane chain is 3 carbon chain, which is propane. Let's look into another example. CH3, CH, CH2, CH3, and you have a chlorine here now. So how do we name this? What is the IUPAC name? Let's number the chain first. So this is your parent chain with a more number of carbons. That's a basic rule. And we number such a way that the carbon with the substitution here is chlorine. So the carbon with substitution gets the least number. So the best way is from left to right, 1, 2, 3, 4. So your halogen here is chlorine, and your carbon chain is 4 carbon chain, so it's a butane, right? So your IUPAC naming is going to be, as I said, what is the IUPAC namings? Will be haloalkanes, right? Haloalkanes. So what is your halogen? It's chlorine. It's a second carbon. It's a 2-chloro. What is your alkane? It's butane, 2-chloro-butane. So that is going to be your IUPAC name. Okay, so the IUPAC name of halogenated alkanes are going to be named as haloalkanes. This is something you guys need to remember. Haloalkanes. It's 2-chlorobutane, 2-bromopropane. Haloalkanes is something you need to remember. The number actually represents where the halogen connected to the parent chain butane. Okay. Now, what about arenes? If you have a benzene ring, for a halogen substituted derivatives of the benzene, the IUPAC names are known as pretty much haloarenes, halobenzene. Okay, let's take a benzene ring. If you put a bromine compound here, so it's going to be halobenzene. Okay, what is your halogen here? So halobenzene is something you guys need to remember here. So it's a halogen, bromine is the halogen here, so it's going to be bromobenzene. If you have iodine, the name is going to be iodobenzene, right? And if you have a chlorine, it's going to be chlorobenzene. So what you guys remember here for arenes like a benzene ring, the IUPAC, also the common name is going to be halobenzene. And also second important thing you need to remember, no numbers, no lactants when you have one halogen on the ring. Okay, so this IUPAC naming on the benzene ring is specifically on when there is only one halogen on the benzene ring. So but what about when we have two halogens? We'll look into that as well. Imagine you have two bromines on the benzene ring. So how do we do this? For IUPAC name, what we're gonna do, we're gonna use the numbers now. So we'll number, so 1, 2, 3, so and 4, 5, 6. Or you can also number the other way. It's a 1, 2, 3, 4, 5, 6. Either way, you have a bromines at 1 and 3 carbons. So it's going to be 1, 3. How many bromines you have? 2. So what is the scientific term we use in IUPAC names for to say 2? Di. And the halogens are bromo, benzene. Okay, so how the way we write, if we have more than one halogens, are we use the numbers, and we use a suffix di or tri Depends on how many halogens, and then we write the halogen and then the benzene ring. Let's look into one more example. We have a chlorine, and chlorine. I'm numbering such a way that the carbon with halogen getting the least number. This is the best way to number the benzene ring. Any other way you number the benzene ring, the substituted carbons get the highest numbers. We always should number the benzene ring such a way that it gets the least numbers. So the IUPAC name for this molecule is going to be, we have 3 chlorines, and what are the positions? 1, 2, and 4. 1, 2, 4. How many we have? 3. The term we use is tri to represent 3, and the halogen is chlorine, so it's going to be chlorobenzene. This is going to be your IUPAC name. So it's 1, 2, 4 trichlorobenzene. All right. If you guys have a minute, you can work on these 2 examples here: CH3, CH, CH3, iodine. Write the IUPAC name for this molecule, and also this molecule. Okay, write the IUPAC for these 2 molecules. This is going to be your homework. So what happens if you have IUPAC name for dihaloalkanes? What happens if alkanes have alkanes with more than 1 halogen? So what do we do in this case? In this case, the dihalo compounds having both the halogen atoms are further classified into geminal halides and vicinal halides. Okay, so a geminal halide, geminal halides. Here, gem means on the same carbon, whereas vicinal carbon, vicinal means on the adjacent carbons. Adjacent carbons. Adjacent carbons means next to each other. For example, for geminal halides, let's take a molecule CH3C, CH3, chlorine, and chlorine. And for vicinal carbons, CH3, CH, CH2, chlorine, and chlorine. In this case, in the first example, you have 2 chlorines on the same carbon, so they are geminal halides. In the second example, the 2 chlorine atoms on the 2 carbons are next to each other, so these are vicinal halides. Okay, so that's how the name you use for geminal, and how you identify geminal and vicinal dihalides. So what about the IUPAC name for these compounds? For these compounds, the IUPAC is going to be we use the numbers. For example, the parent chain here is going to be, I use a different color. This 3-carbon chain is the parent chain in both cases. But what about numbers? In this case, we're going to number whether from left to right or right to left, it's going to be the same. So you have 2 chlorine atoms at a carbon number 2. So the IUPAC name is going to be 2,2-dichloropropane. Okay. And for the other compound here, the numbering is going to be 1, 2, 3. It's going to be from right to left this way. And if you're doing from left to right this way, this is wrong because the carbons, the substitutions get the highest number that way. So the right way is doing from right to left. So the IUPAC name is going to be, for this compound, we have 2 chlorines, one on the carbon number 1 and carbon number 2. So it's going to be 1,2-dichloro, and the parent chain is propane. So remember, the IUPAC name should be efficient enough to recognize the molecule. If you look at the IUPAC name, you should be able to write the structure. So that's why you have to learn and be efficient in writing IUPAC names. So here is the homework. Write the structures for 3-bromohexane. Write the structure, and for other one, I'm giving you structure. So for this, write the IUPAC name. So this way you guys practice both. For the first one, I gave you the IUPAC, write the structure, and for the second one, I gave you the structure, write the IUPAC name. All right, the next thing we look into is nature of CX bond. Nature of CX bond. So what is a bond? Actually, we studied, you guys have studied in previous classes, when you have a carbon and halogen, X is any halogen, could be fluorine, chlorine, bromine, iodine, any halogen. Here, halogens are high electronegative, so they possess electronegative charge, and that causes a partial positive charge on the carbon. So, which means the bonded electrons in that bond usually pulled more towards the halogen. There is an inductive effect because of high electronegative halogen atoms. X is high electronegative atom in a CX bond. So the carbon always partially positively charged, and the positive charged atoms usually called electrophilic in nature, electrophile, Either they are partially positively charged or completely positively charged. For example, here, in this case, the carbon is electrophile. Okay. Now, we use other term, nucleophile. Nucleophile in any bond, any atom which is in partially negatively charged or completely negative charged. It's known as electrophile. So in this case, the halogen here is, nucleophile. In this between carbon and halogen, your halogen is nucleophile. Okay, these are really important terms to remember. And if you could identify electrophiles and nucleophiles in any chemical reaction, the chemistry is between a nucleophile and an electrophile. Any chemical reaction, you pick any chemical reaction, the reaction always happen between nucleophile and electrophile. Okay, because nucleophile is something electron rich and electrophile is electron deficient. So the nucleophile always attacks electrophile in an organic chemistry or the chemical reactions. So if you have the basic understanding about electrophile and nucleophile, it makes it really easy for you to learn the organic chemistry in future. Okay. So that's the nature of the CX carbon halogen bond. Then what about bond lengths? If you want to look into the bond lengths, it's easy to correlate the bond lengths for different halogens. Okay. In a periodic table, the halogens are on the far right side of the periodic table, and they are fluorine, chlorine, bromine, iodine. So what happens to the size when it's in the periodic table from top to bottom? What happened to the size of any atom in the periodic table? If you go from top to bottom, the size actually increases, right? So imagine when you have carbon same in each case, but fluorine is way smaller, chlorine is bigger, bromine is much bigger, and iodine is much bigger. The bond length is nothing but distance between the nucleus of the two atoms in each case. Okay, so imagine this is carbon fluorine bond, this is carbon chlorine bond, this is carbon bromine bond, carbon iodine bond. Now what is happening between the distance between the two nucleuses when the size is increasing? The bond length usually increases. Okay, the bond length increases with when the size of the halogen increases. When the bond length increases, bond strength becomes weak. Okay, let me explain that again. When the size is increasing, the bond length increases. When the bond length increases, the bond strength decreases. The bond strength is nothing but how strong the bond between the two atoms. Okay, so if between carbon and fluorine and carbon and iodine, the bond length here is small, the bond length here on the far right is far more than carbon fluorine. Since the bond length is short here, the bond between these two atoms is really strong. The electrons are holded with such a strong force compared to carbon iodine. So that's why bond breaking here is difficult. It takes lots of energy. But bond breaking between carbon and iodine is easy because the length is more. So that's the correlation between bond length and bond strength. If you guys look into any table that comparing bond lengths and bond enthalpies, The enthalpy is nothing but bond, the energy it takes to create or make that bond. So the relation between bond length and bond energy or enthalpy, it is inversely proportional. So if bond length increases, bond energy decreases. So this is something you guys need to remember. Next, we look into preparations of alkyl halides. In the preparations, the preparation we use 3 different chemicals here, especially. Those are the main compounds that we use. Our first chemical compounds we use are alcohols. Okay, alcohols to alkyl halides. We also use alkanes, and we convert them into alkyl halides. And we can use alkenes, and we can also convert alkenes into alkyl halides. There are 2 different ways to do this. We'll look into them later. And there are some specific reactions, name reactions that you guys have. Electrophilic substitution, and also an important reaction called Sandmeyer reaction. In Sandmeyer reaction, you have amines, aromatic amines converts into diazonium halides first. And then those benzene diazonium halides can convert into aryl halides. So these are pretty much, so other one is aromatic electrophilic substitution reactions, where you take a benzene molecule and convert it into aryl halide. So these are major preparation methods. You can take alcohols and convert into alkyl halides. You can convert alkanes into alkyl halides. You can take alkenes. Alkenes means there is one double bond between carbons in any alkane, which is alkene. And aromatic amines can be converted into aryl halides, which is a Sandmeyer reaction. This is Sandmeyer's reaction. This is one of the named reaction. And you can also convert benzene into aryl halides. These are preparation methods. In organic chemistry, the way you're supposed to study, even though you're studying these reactions here, you probably see at least one reaction for each in this unit. This is also comes under reactivities of alcohols. For example, any reaction you study in the category of converting alcohol to alkyl halides, here this is preparation of alkyl halides. But when you're studying alcohols, the same reaction you can use in the reactions of alcohols, right? This is also a reaction of alcohol. For example, any alcohol, let's take an example of alcohol to alkyl halide. Okay, so if you take an alcohol like ROH and use POCl, PCl5 pentachloride or sulfonyl chloride, like trying to come up with a reaction, like take an ethanol, for example, CH3CH2OH, and if you treat this with thionyl chloride, SOCl2, this gives you apparently CH3CH2. Here the chlorine is what substituted alcohol here, and then it produces sulfur dioxide gas and HCl gas, apparently. So in this reaction, the alcohol converting into alkyl halide, what I'm trying to say is you can study the same reaction under the reactions of alcohols. In Unit 11, when you're studying the reactions of alcohols, this probably come again. So you may see reactions, same reaction multiple times. That does not necessarily mean we are studying the same thing again and again, but we are studying the reaction from a different perspective. The perspective here is how we can synthesize alkyl halides using alcohols. So this comes under preparations of alkyl halide. Okay, all right. So what kind of halogenated reagents we could use in these kind of reactions? So anytime you have an alcohol to convert into the chloride, the kind of halogenated reagents that you could use, you can use HCl in combination with zinc chloride. You can use PCl3 or PCl5. You can use thionyl chloride, just like we saw, or you can also use a red phosphorus in combination with chlorine or bromine. Okay, when I said a chlorine or bromine, if you use chlorine, the alcohol converts into RCl. If you use bromine, the alcohol converts into RBr. Okay, so these are halogenated reagent that you could use. The first thing, HCl in presence of zinc chloride. The second one, PCl3 or PCl5, phosphorus reagent. Then sulfur reagents or thionyl chloride, and a solid state catalyzed reaction with red phosphorus and using chlorine or bromine gases. Okay, so these are different kinds of reactions that you could use. If you want to look into reactions, one example for each type, I'm going to write here. I'm going to use ethanol in each case with the HCl and zinc chloride. We're going to convert this into 1-chloroethane, plus we produce water in this case. Okay, and the second reaction, if we use PCl3, you can produce CH3 CH2 Cl plus H3PO3 phosphoric acid. And if you use ethanol and PCl5, you can produce CH3 CH2 Cl and POCl3 plus HCl And we just saw the reaction with the thionyl chloride here. So you can use the same reaction. CH3, CH2OH, the thionyl chloride SOCl2, that gives you chlorinated alkane and SO2 and HCl. Okay. So, I mean, these are why different reactions that we studied. Not all the reactions conducted in the same way, but these are a few reactions that you could study. Conversion of alcohols to alkyl halides. I recommend you guys practice these reactions because you can use these reactions at two different places. In this chapter, in this unit, under preparation of alkyl halides, and the next unit you can use it under reactions of alcohols. Okay. From alkanes, so how can we synthesize alkyl halides from alkanes? So this is so far we studied under alcohols. Now from alkanes to alkyl halides. This is one interesting way to make alkyl halides from alkanes, because we use UV light or heat in these kind of reactions. The reaction go through a radical halogenation pathway here. Let's take an example of butane. CH3, CH2, CH2, CH3, and any halogen that we take, for example, chlorine, under UV light, which is a sunlight, or you can use a UV light source, or you can also use heat, just pure heat without any solvent that we are talking about here. All right, so we can actually do halogenation here. The halogenation pathway is something, the mechanism is something we don't discuss, at least here at this part right now, but the halogenation can happen at multiple carbons. It can happen at the terminal carbon, or it can also happen at the internal carbon. See, if you see the way the halogenation happen, it can happen at the terminal carbon. The 1 and 4 carbons are pretty much same here. 1 and 4 are pretty much same. So the halogenation can happen at one of these, and the 2 and 3 pretty much same. So the halogenation can happen at 2 or 3 carbon. So what is the difference between 1, 4 and 2, 3? 1, 4 carbons are their primary carbons. They are primary. 2 and 3, they are secondary carbons. So the halogenation can happen at primary carbon. It can also happen secondary carbon. So you will get combination of two products here, alkyl halides. So is this an efficient way to make alkyl halides? We are not discussing this here, because you will get combination of two products here. If you need specifically one product, it's really hard to get such product here, because these reactions typically produce combination of two products. Okay. So the next way to make alkyl halides are from alkenes. From alkenes to alkyl halides. So alkenes are pretty much any carbon with a double bond. Any alkane with a double bond is pretty much alkene, right? So there are two reactions that we can do here. All right. So we can add a hydrohalide reaction. We can do a hydrohalide reaction like a HCl or HBr, which means you're adding, by the way, you get rid of a double bond. Okay, so you add one hydrogen, one halogen in these reactions. These are halide reaction. Okay, it's called hydrohalogenation. It's in the name, actually. If you look at the name, it's hydro means a hydrogen, halogenation means any halogen. The X could be chlorine or bromine, or depends on any halogen, the hydrohalogen you have. Okay, so hydrohalogen means addition of one hydrogen and one halogen to alkene in this case. So this is one way of preparing alkyl halides. So there is one rule that we're supposed to discuss, like how the hydrogen halogenation happens. So the alkene carbon, these two are the alkene carbons. In this case, this alkene is pretty much symmetrical, which means both carbons looks pretty much same. What about unsymmetrical carbon? For example, if you have CH3, CH double bond, CH2. Yeah, this is a nice example. I mean, first thing, whenever you're doing a hydrohalogenation, let's add a HCl to this alkene. First, you need to identify the two alkene carbons. The carbon with double bonds are alkene carbons. Now, which carbon gets hydrogen, which carbon gets halogen is the case we are going to discuss. The carbon with the more number of hydrogens between these two alkenes, look at the carbon here. This carbon directly connected to two hydrogens. This carbon on the left side, it only has one hydrogen, right? I mean, think about it. Spend a minute to understand what I'm trying to say here. All you need to do is pick the two alkene carbons and see how many hydrogens on each carbon. The carbon with more number of hydrogens gets the hydrogen. So the product is going to be CH3, CH. So go ahead, write the reagent first without the double bond, CH2. Now, as I said, the carbon with the more number of hydrogens gets the hydrogen, and other carbon with an alkene gets the halogen. Okay, this is the rule. If you write it other way, that is not the major product you get. Okay, so this rule is known as Markovnikov rule. Okay, so what does Markovnikov's rule say? In Markovnikov rule, when you add a hydrogen and halogen to a double bond, the hydrogen goes to carbon with more number of hydrogens, and the halogen goes to carbon with the least number of hydrogens. Okay, let's look into another example. Carbon here, a hydrogen, CH3, CH3 double bond, CH3. Now let's see, let's add HBr to this alkene. Now, what did they say? The first thing is to identify the alkene carbons. These two are the alkene carbons. Now identify the hydrogens. This carbon here has 0 hydrogens. When I said hydrogen, the hydrogens directly connected to that carbon. For this carbon, there is only 1 hydrogen. So among these two, the one on the right side has more number of hydrogens. So when you write the product, just write the reagent without the double bond. And where you write the hydrogen, hydrogen goes to carbon with more number of hydrogens, and the halogen goes to carbon with least number of hydrogens. The halogen here is bromine. So that's your product. This is going to be your major product, and this is also called Markovnikov's product. Okay. It's a simple logic why it's called Markovnikov product, because the product is formed following the Markovnikov rule. That's why it's called Markovnikov product. Okay. So there is also possibility to form other product like this, which is completely opposite to what Markovnikov said. And if this is product, this product is called anti-Markovnikov product. Why it's called anti-Markovnikov product? Because it is not following Markovnikov's rule. It is going against, it is forming an opposite to Markovnikov product. That's why it's called anti-Markovnikov product. So the next scenario is going to be addition of halogens. So far within alkenes, conversion of alkene to alkyl halides, what we studied, hydrohalogenation is what we studied. So the second scenario is addition of a halogen. So simply a pure halogen like X2. So it could be bromination or chlorination or whatever halogen is available. Okay. So in this case, the halogen, one halogen goes to each carbon. Okay. So the product is going to be RCH, CH, R. You get rid of the double bond and you get X and X. So it's a dihalo product. Is this the geminal halo product or vicinal? Do you guys remember geminal and vicinal halogenation? Yeah, here. Geminal. Geminal means when the halogens on the same carbon. Vicinal means when the halogens on the adjacent carbons. So what you're making here in this case, the halogens are on the adjacent carbon. So in this method, addition of halogens addition of halogens to alkene always gives you vicinal dihalide compound.